first part, so let's run through that very quickly. Let's check those answers, and then today we're going to wrap up these notes here. And wrapping up these notes, we've already gone through the first half of it, of why these triangles are turning out to be similar by our shortcuts, and then the second half of notes today is going to continue with using the applications, or doing the applications with similar triangles. So let's really quick kind of jump into here on that front side of things. So on that first few questions there, what shortcut might we say try to use out of this? Is I'm looking at that first one there. If it's gonna say happen on that first one there, it would have been happening probably by SAS if it's going to happen off that one. So as we've talked with those, you're going to separate the two triangles. And as we separate those two triangles, all right, what do we have? C what? MP. And what's my two side lengths? 12 and 21. And then what? 20 and, what is that, 35? So as we did yesterday, we saw in our notes, we did this one already, but with this here, does the sides turn out to be proportional? So what's that become? 3/5. And then what's the other one become? Reduced by 3, what's that become? 7/5? Reduced by 7, which is, yep, thank you, Sam. Reduced by 7, which is 3/5. I had that reversed in my head. So the sides are proportional, and then as we said, the C is in both of those. So it's got to be that angle between those two sides. So does side angle side similarity work on this one? You should have said yeah. And then because of that, at some point here on, I guess at the bottom there is where you're saying that, or maybe, I don't know. Just say, make sure at some place say side angle side similarity. Name the two triangles. TQC starts it, so then you better go in the correct order there. TQC goes with what? PMC. And if I don't know if I asked you state, you didn't say state the ratio, I don't think, but always state the ratio plus here. In this case, it is 3/5 like we've been doing, okay? The other one should have been the quickest one there, AAA similarity. All right, that's happening, and AA, whatever, AA similarity. AA similarity, and on that one there, it would not have been possible to state the similarity ratio and then correctly name that one. If we went with XYZ right here, what does X go with? 1 to 1 is E, XY, Y is nothing, so what's nothing? N, double is Z, and what's double? W. So if you got those going, then you're good from yesterday on the shortcuts. Down below, all right, number 3, a little bit of a awkward looking one. Okay, so as we look at this kind of awkward looking one, all right, on this one, this is one where we might want to kind of do the separation of the triangles. What I'm seeing here for myself, first thing is A is corresponding to which one? E, yeah, A is corresponding to E. So I've got that going. Angle A is congruent to angle E. But then after that, I've got some separation I want to do here. What I'm going to do then is, keeping in mind A is going to come to E, and then when I separate these, that smaller one, I'm trying to envision in my head as I separate that, A is coming down to E, and where's that D going to eventually match up to? What angle is D going to try to match up to? Yeah, D is going to match up to C, so I'm going to redraw this matching up the same orientation. So that big triangle, I'm going to leave in that same orientation of A, C, and B. All right, so there's that marking. But it's that smaller triangle that's kind of a little bit awkward. And I'm going to redraw that, again, kind of that same orientation where this is E. And I'm kind of imagining flipping that D around. So D is imagine C. And what's going to be true about B? B is B, right? And because B is B, What can we say about that? Because B is the same, what's actually true here? Which one's working for us? Angle's working here. So this one here is similar. It's not a quick and obvious one, or at least maybe for me it was not quick and obvious here, but it is angle similarity happening on this one. Just because you do have to do a bit of a kind of reflection and a little bit of disorientation off that one. So this is an angle similarity. And when I kind of rearrange things, what do we have? DBE, and rearranging, flipping it around, DBE goes with what? Triangle CBA. Okay. That one's probably the trickiest of the group there, I think, just because of that awkward orientation. So again, look for something that matches up, kind of links it all together. E and A was the first thing that again jumps out to me. And then the other thing, just because I've done it for years, is that B is overlapping in both of those. So I reflected that and got that D and C kind of in that same location. Last one there, there's my bow tie. And as we said yesterday with the bow tie picture, one of the first things to always mark up is our vertical angles. Okay. And with those vertical angles, we've got these sides. 12 corresponds to 24, which reduces down to, I'm looking for halves. And does 15 reduce to 15 over 16 become a half? Not quite, does it? So are we proportional? So can we do a similarity statement? And can we use one of our shortcuts? So we are not similar, and tell me what failed. What failed? Sides are not proportional. Okay? So that was what we talked about yesterday. Okay? If you get those, if you did 1, 2, and 4, I'm happy. Number 3 is an awkward one. If you get 1, 2, and 4 going, then you're cool from yesterday. Okay? Those are the kind of straightforward ones. 3 is a little weird, but if you got 1, 2, and 4, you should be good to go. Okay? Now the rest of those at the bottom, number 5. Number 5 obviously is not a triangle. Number 5 is take us back to what we did on Tuesday. It's a quadrilateral. So what you do need to do on number 5 is everything working? Is all the corresponding angles congruent? Or all the corresponding sides proportional? You have to do everything in all the same. So when you look at all these, are all the corresponding angles congruent? Can you match them all up? Yeah, yeah, yeah. Okay, all the corresponding angles congruent. Are all the corresponding sides proportional? We got Alan shaking her head here. 4 to 2 seems to get to me to 2. 7 to 3.5 depends on how great your kind of just arithmetic skills are. But 7 to 3.5 does become 2. 6 to 3 does become 2. And what's my last pair? 5 to 2.5 also becomes 2. So corresponding angles congruent, corresponding sides are proportional. Do we have similar figures here? Sure do. Okay, and because we have similar figures, you can state similarity statement. Name the first one. We do a lot of triangles. Who cares? It's a quadrilateral. Name it. Go simple. Go with the obvious. What's the obvious name for that first one? Yeah, ABCD is similar to, and then walk it around and make sure ABCD goes correctly. If I go with ABCD, I'm going with EFGH. And what's my similarity ratio? 2 to 1, 2, 2 over 1. I don't care. It all's fine there. Okay. Good old distance formula. Again, I mean, just kind of keep throwing that out there for you. It's just good practice with the distance formula. Just one of those things that we just kind of continue to use in Algebra 2 next year. You'll continue to use the distance formula in a few applications through there. And then lastly, down at the bottom, just some, again, older stuff with doing some more proportions with number 7 there. Setting up the proportion, which you guys did fine on. Using that proportion of 1 inch makes up 15 feet. And with that, what do we want to do? 48 feet. So where's that 48 feet got to go? Numerator, denominator. And we got to figure that out for the inches. So that's my variable. And you guys are fine with cross products now. So again, we got some. You guys are good on cross products. I don't care about that. You guys are fine there. Okay. It doesn't look like it comes out to be nice, does it? So if it doesn't come out to be necessarily nice, if it doesn't really tell you where to round, again, our default is to go ahead and, I guess 3.2. So default would be to go ahead to the nearest tenth. All right. And we'll do more work with that as we get into trig, about rounding issues with trigonometry. We'll talk about that, which is just around the corner. Okay. All right, on that last one, two squares are similar. Always, sometimes, are never true. Two squares are similar. That's definitely the case. All right, two squares are similar. That's always the case. All right. The corresponding angles are always going to be congruent, and the corresponding sides will always be proportional. You might have a square that's all twos around, and the other square might be all fives around. The angles are always 90, and the sides are always going to be proportional. Two hexagons are similar. Okay. That one, it just depends. What I mean, it just depends. Depends on what type of hexagon that is. Okay. In terms of a hexagon, they did not put in there the word of regular, if I could spell regular correct. Okay. If they said the word regular, then that would have been fine. So hexagons, difference from squares. Squares are 90 degrees, but a hexagon, it could be where they all are a nice shape. Looking at my shapes here, okay. So there's my hexagons, okay, where they're all 120 degrees at the angles, but that's a nice regular hexagon. If it doesn't have to be a nice regular hexagon, we saw hexagons that do not have nice 120 degrees. So letter B, sometimes. Sometimes is the issue, okay, because they didn't put the word regular in there. So it just depends on the hexagon you're dealing with. Okay. All right. We'll leave it at that. Anybody else have any other quick questions there? That really kind of covers probably the biggest ones I wanted to talk about. All right. Make sure your name's on it, throw in the basket. Let's finish up these notes today, boys and girls. Get out those notes. Pencils and calculators for sure. And let's continue to do our work with proportions here. Okay. Give you a minute, get your life situated. Pencils and calculators, everybody. Pencils and calculators out. Okay. Now, after today, again, we wrap up everything. Next week, we'll come in Monday. We'll go over questions. We'll work on our quiz review. We'll go over that Tuesday, Friday, and then that will be it. It's a full week next week, and then the following week is 4-day week with good old Cashman Pulaski Day. And then also at the end of that following week is the end of, again, the third quarter. So it's not too far away here. Okay. All right. Again, we are using our shortcuts today for similar triangles. Doing applications with this, and this, again, last lesson here rolls us right into trigonometry and special right triangles that I keep talking to you about. It's going to be a continuation here. The difference is going to be, I'm going to take away some of this information where I'm not going to give you enough information where you can't do proportions. So how do we deal with that? I give you different types of information, and that's where trig comes into play. All right, so let's take a look at that. Take a minute. Let's read through that first question here, where we just got some more stuff we've already been doing with that proportion, setting them up. But the biggest thing is, can you read and draw and label out the picture which being is described? That's always the roughest part. It's not setting up the proportion, it's just reading and figuring out what is being described off of there. So we've started that. Let's take it and go with it again here. So take a minute if you haven't done so yet. Okay, so most flagpoles we know are standing perpendicular to the ground, but in this instance here, not all flagpoles are, especially after the years, kind of get not all upright. So some what we say is oblique. So an oblique, we'll talk about that as we get into some work with volume later on. An oblique here is where it's not nice and straight. It's not perpendicular to the ground. It's got a little bit of a lean to it. All right, think of like Michael Jackson there. All right, got a bit of oblique here. So imagine an oblique flagpole in front of an abandoned building. Question is, can we use sunlight and shadows to determine the length of the flagpole? So assume here we know the following information. The length of the shadow of the flagpole is 15 feet. So shadows we know occur along the ground. So we got our ground as that parallelogram there. There's our flagpole sticking out of the ground. There's a mark on the flagpole, all right, 3 feet from its base. So what do we mean by mark on the flagpole? Think about the tie off on the rope of the flagpole here, somewhere about 3 feet right there on the flagpole from its base. The length of the shadow of this 3 feet portion is 1.7 feet. Knowing those few pieces of information, all right, can we determine the length of that flagpole? And yeah, we can. So let's just go ahead and start throwing out the information that we got off that, okay? So from here, okay, so as the sun's rays come casting down here, okay, we got shadows that come casting down here. Shadows occur along the ground, okay? So as we got that coming down then, what's this shadow's length? Shadow's length is 15 feet right here. So shadows occur along the ground, okay? And this is why I was saying here, the mark on the flagpole is 3 feet from its base. Half the battle is just kind of visualizing what does that mean. So again, think of on a flagpole where you tie off the rope on the flagpole. There's a cleat usually right about there that you tie it off. That's what they're kind of referring to. So that little cleat right there is what? 3 feet high off from the base. And that little bitty piece, okay, that casts a little bitty shadow that we're able to see kind of protruding out. That only goes of a shadow, how much? It says 1.7. So that's also creating just a little bitty, whatchamacallit, a little bitty shadow that we can kind of tell. That's, you know, sometimes you can kind of see little things that protrude out on the shadow there. And from there, we do have enough kind of information happening out of that. So what's happening here is AA similarity. Actually, probably most of these that we're going to look at are happening from AA similarity. Where that's happening from AA similarity is coming from, first off, the sun's rays casting down. As the sun's rays cast down, the way that this angle comes down is this angle right here. As those sun's rays come down to create that shadow with the ground, that angle is the same. Okay, so there's one angle. The other angle that's being created is this overlapping one right here at the flagpole. As we separate these two triangles, these two angles right here at the flagpole, it's the same angle, right? We've seen that multiple times here recently. So these two right here are the same angle. So I'll separate these two triangles. We've done it quite enough where it probably isn't necessary, but we've got that shared angle here with a 3 and a 1.7. Now my bigger triangle, and that is going to be the height that I'm trying to find. This is the big length of the flagpole. I don't know. Let me call that H right now. And what's the 15, right? And so that's what is happening here. AA similarity tends to be our go-to one that we pretty much do everything with, actually. Now, setting up the portion is pretty usually dang easy. It's just labeling and setting up the picture is the biggest part of it, okay? So match it up. How you write the proportion, I don't care, all right? I just usually start with the variable. H corresponds to 3, and what goes with what then? 15 to 1.7. So then let's go at it. Cross products we go. What we got? 1.7H. And what? 15 times 3 is 45. Go to your calculator if you haven't done so yet. And what do we got? 45 divided by 1.7. What do we got? And does it say what around? I don't see anything, do we? So our default will be nearest 10th. Okay, so 26.5. And we have units, I believe. 26.5 feet. Okay. So 20, and then just do a logic check. Okay. My daughter right now, she's in 3rd grade. She's learning about measurement for the first time. And then 3rd grade is about where you start to kind of just do logic checks, meaning what makes sense for the height of a door, what makes sense for, in this case, a length of a flagpole. That's where you start learning about measurement. And I can buy about a 27-foot flagpole. That seems to be kind of makes sense. You guys know what 27 feet kind of look like. So do a logic check on some of those. Okay. All right, let's roll with this. Take number 5. Read through that. All right, on number 5, and let me try to shrink that down a bit. And then let's take what we've got there and let's label it into that picture. Okay. Give you about a minute. Read through that if you haven't done so yet. And label out what's there. All right. Don't wait on me. You got to label these out yourself. So really part B is where it's kind of going to be at. As you read through there and get to part B where all that label information is going to be at, can you correctly label out where that is? Again, those numbers are going to be going. All right. And part A is kind of, again, where that's at. It says, hey, these are similar triangles. Why are they similar triangles? And if you're able to say why they're similar triangles, what that usually tells me then is I'm going to be able to probably set up some type of proportion, assuming I have enough information in this problem. Okay. And most of the time, the reason why we're able to say set up proportions is it's all about AA similarity. As I said earlier the other day, you may not care why we can set proportions, but it's because of AA similarity why we're able to do trig very nicely and all these proportions. It usually goes back to AA similarity. So the reason why we have similar triangles in this particular problem, as they were saying, okay, we go ahead here as they stated there. Okay, if you put a mirror at a certain spot and walk back enough to where you walk back enough here and put that mirror at a spot and you look at and you can spot the top of the building, the way that that mirror the spot, excuse me if I can speak, the way that that image bounces off the mirror and you can see the top of that building at that particular angle. Okay, that angle as it bounces back off that mirror and looks into your eyes, that is the exact same angle. Okay, so that is why they're showing it is at congruence, 36 degrees. Where does that other angle come into play? I gotta have two angles up there to be AA similarity. Where does that other angle come into play? We always assume that you and the building are perpendicular to the ground. Okay, so we have one kind of a small assumption that's happening there, that the building and you are standing perpendicular to the ground. So we roll into special rights and trig. Same thing's going to be happening there. So why do we have this happening? It's because of AA similarity. We have no side information at this time, do we? Now we have AA similarity working. All right, where'd you start putting the information at? Okay, what's our first piece of info? 5.3. Distance from eye level straight down to the ground is 5.3. So let me just put some letters up here. Let me put letters and not like numbers. A, B, C, D, E, and F. Okay, somebody, where's 5.3 going? A, B, C, D, E, F. Not quite C. It says distance from eye level straight down to the ground. That is Parker. That is A. Basically, what is that representing? That is basically your height. Okay. So straight down to the ground, that's your eye level. That's essentially your height. So height is going right there. Okay. Okay. Next part. Distance from the person to the mirror is 7.2. So we took out A. There's 7.2 gone. B. Okay. So B is 7.2. All right. The distance from the person to the base of the building. Where's that going? Almost E. Not F. Shut up. Okay. It's actually a combination of what? E and the 7.2. Because what's it say? The distance from where's the person at? And where's the base of the building at? Okay. So we need to say that is 1750 right there. It's the whole length right there. But what I need to figure out then is that's the whole part. Those are both triangles together. I only need the one triangle. Brianna said E. I only need E though. Right now I have that 7.2 in there. So what do I need to do to get rid of that 7.2? Subtract it out, right? So 1750 minus 7.2 gets me E. So E is going to be 1742.8. That is a nice SAT question they're going to do. C and D, I got no information about it. Erase them. They have nothing to do with this problem. Because what do I want to try to find here? The height of the building, which is represented by X. Now I called it F. Who cares? Okay. Height of the building is X. We are good to go. Now, we just actually calculated that without looking at that question. The distance from the mirror to the building was at 1742.8. What is this, feet? And we're good to go. We have everything corresponding sides matching up. You guys can set the proportion out. That's the easy part. Setting up the proportion is easy. Taking the information, reading what it says, putting it in the right spots. And on this one, the right spot was realizing where's that 1750 doing. You had to do a subtraction on that. Now we've done some additions before, but maybe a little bit of subtraction. I don't know. I don't remember. All right, set up your proportion if you haven't done so yet. I always start usually with the variable at this time in the proportions of applications. X corresponds to height of the building, height of the person. And then since I start off with the X, I'm going to start off with 1742.8. So 1742.8 to 7.2. Again, this is why you got to have calculators. Cross products we go. 7.2x. And if you can do that in your head, more power to you. But more power to you. 5.3. So check my calculators as well. It's easy mistakes. And then we're going to divide by 7.2, right? All right, somebody get, and does it say what around? Yeah, it doesn't say what around, so we'll just go with our default. So 1,282.9. Okay, feet. Now, does that 0.9 probably really matter? No. Okay, probably what the SAT would do at this time, they'll probably just run that to 83, 1,283 feet. Okay, but we'll just keep it with the 0.9. All right. All right. Let's keep rolling here. Let's flip it to the next side. Take a minute, read that next one up there. Okay. let's see, do I like that one? Let's go to number 7 actually. Okay? Or do number 7 with you. Okay, take a look at number 7. It's another one here. Take a minute, read through number 7. I like you to do the same thing here. I'll come back in a minute here, label it out with you. But I like you to read through number 7, label out that picture. Okay? Label out that picture. This is a 2-part question on the SAT. This is a 2-parter SAT question. Let's do this one first. Okay. So as I said, SAT, this is a 2-parter. SAT doesn't usually have too many questions that are 2 parts. Usually it's just 1 question and done. But this one here has a 2-part question. It's using the same question for 2 parts. First one here is doing exactly what it's asking. How tall must this tree grow to eventually provide shade for the house? So this family is playing the long-term game. Okay, as we know, trees provide shade, and when it eventually provides enough shade for this house, what does it do for your electrical bills? Eventually, it does lower your electrical bills because it's providing shade on the interior. Okay. Now, half the problem with SAT is just reading and what is it sometimes saying, and I usually have to read through it a couple times. It's just me. All right. Assume that the sun casts a shadow 32 feet long from. All right. So that shadow's casting a. So that sun's casting a shadow from the top of a house to a point in front of the house. So that's where that shadow's coming from. From this part of the house, that's where that shadow's happening then. So here's that shadow that's happening from that point. And what do they say it is? 32 feet long. Okay. Now, the distance from the end of the shadow's house, at the end of the house's shadow, to the base of the tree is 53. So the end of the shadow to the base of the tree is 53. Okay, if the house is 16 feet tall, we got that. All right, 16 feet. How tall must the tree get to provide shade for the house? So eventually we want this tree to get tall enough, okay, to provide shade for that house. So as we do that, and as I sketch mine out, hopefully you're seeing, as I sketch mine, because I've done this for a long time, you see that we got ourselves 2 triangles happening now, okay? And the reason why this is happening is we got a similarity. Where's the A similarity coming from? These are sharing this same angle right down here where that shadow is occurring. And we're assuming that that tree and that house is at a right angle. So a right angle and a right angle to use AA similarity. I'm going to separate these 2 triangles, okay? So when I separate these 2 triangles, this is essentially what we're breaking it down to. 16 and 32. And here's my tree eventually that I want to get growing. That's basically what it boils down to. Okay. Reading through that, not necessarily the easiest to read through, but that's what it boils down to with the SAT. Now, again, writing the proportions easy, but setting it up that's the name of the game. H to 16 is then what? 53 to 32. Again, you don't have to set up your proportion like that. Just be consistent. Go to our calculator. All right, 32H equals 16 times 53, 848, divided by 32. Somebody get 26.5?
Yes.
And what's my units? So eventually that house is, that tree's gonna need to get to be, 26 and a half feet. So right before that, maybe about 24, 20 feet, probably will start to get some type of protection. That 26 and a half feet is where we'll see that we'll get that full shade on that house. Now the follow-up question is right here. How long is that gonna take you to get there? All right, so you bought a tree there, Market Basket or anything. The tree is, at the moment, you bought it at 7 feet tall. And you know to get that full shade, it's going to take it to be 26 and a half feet. How long are you going to take it to, how many years it's going to take to get there? The tree that you purchased, you look at the tag of it, that gives you the information of how long, what the projected growth rate is. Okay, so this is going back to now what we just kind of been doing in my algebra classes, our linear applications. Sam, you get an answer for me? Or something else? If it's an answer or just a question?
It's a question about the
answer. Oh, the 26?
For B.
Oh, give me through that, and then I'll talk about the answer, okay? So, you can do this one of two ways. For backfilling an algebra part, you can just kind of play that game of figuring out how to get to 26 and a half feet when you start off at 7. So think about that. 26 and a half feet, you start off at 7. How many more feet do I have to grow? How many more feet do we have to grow? 26 and a half minus 7 is 19 something, right? 19 and a half feet. And 19 and a half feet, and it grows 2.5 feet per year. What's 19 and a half divided by 2.5? 7.8, thank you. So 19 and a half divided by 2.5 is 7.8 years. That's just kind of you playing around with that in your head, just doing some common sense type things. Algebraically, what we do in our Algebra 1 classes, at 7th and 8th grade classes, we set it up like this. How do you get this 26 and a half? Well, you started off with 7 feet. You know you grow at 2.5 feet per year. You solve for x. This is our use of y equals mx plus b. That should ring a bell. Y equals ax plus b. It's the same idea right there. Okay. So it's going to take you about 8 years to get to that point. Yes, sir.
So I just did 2.5 times 8. You got 20 because I don't know anyone that says 7.8 years.
Right. So roughly, and now SAT is going to probably have a couple different ways to say that, or they might have this as that grid response that we've seen, and they will take 7.8, possibly 8 as well. They grid response, they'll give you a couple different options off that. All right, let's go with the last one then. On the last one, what do we got there? We want to find x. It's not proportions. It's just a good one to throw in to wrap everything up with. The only thing we know how to do with the right triangle is still the Pythagorean theorem. That's about to change after this last lesson. Okay? So we know how to do Pythagorean theorem. So let's do Pythagorean theorem here. Okay, let's throw everything out we did with proportions. Which is sides by hypotenuse. So a squared plus b squared equals c squared. All right, what's x minus 2 squared? Let's do everything that we've been talking about with factoring here. This is a factoring one, okay? So as we started off this topic with come back to factoring with proportions, we're going to finish this one factoring with Pythagorean theorem. Take x minus 2 off to the side. When we did polynomials back in first semester, I had a good chunk of you say, hey, it's just x minus 4 or x plus 4. And I said, no, it's not, because you can't kind of just like distribute and say it's a shortcut. You forget this linear term right here. So take it off to the side, multiply it out, and when you multiply it out correctly, you should get x squared minus 4x plus 4. Now, after that, this is what we've been doing with proportions here, but in standard form. You got x squareds. Are those x squareds going to cancel out at any time? Nope. I'm going to put this in standard form, set it to 0, subtract 100. 4 minus 100 is negative. And that's kind of a huge number to have to work with. It's doable. So what do we always look for before I start saying factors of A and C? I look for my, and I have a GCF, 2. I bring out a 2. It brings down the size of my numbers. X squared, take out that 2, and 96 divided by 2 is, and I would much rather deal with A is 1, B is 2, negative 2, and C is negative 48. And this time of the game, you guys have demonstrated that you guys can factor that like that. You're pretty good at factoring A is 1. All right. Factors of 48 that give me a 2. Factors of 48 that give me a 2. 6 and 8. Finish it off for me. So that's the use of our factoring. Heading into Pythagorean theorem and special rights of trigonometry. Okay. So for today, all right, here it comes. This is it. Monday we'll go over things. All right, guys. Yeah, it's just one of those days where it just took us some time to get through.